Well, to continue with our discussions, where we had ended in the last class was I had derived the Clausius-Clapeyron equation from the Clausius equation, and the final derivation where I ended was the Clausius-Clapeyron equation expressed in this particular form. And we find that a more popular equation which relates vapor pressure with temperature is just an empirical modification of the Clausius-Clapeyron equation. In fact, that equation you must have heard, and that equation is much more popular and that is used much more frequently. It is an empirical modification of the Clausius-Clapeyron equation, which is expressed as log 10 b equals to a minus b by t plus c. In this equation, if you this equation is known as the Antoine equation, and for most of the purpose we find that if we have to find out the vapor pressure at some temperature, or if we want to find out the boiling point at some particular pressure, usually we use this particular equation. If you compare the two, we find that there are basically two differences. One is it is expressed in log 10, whereas this is with the 10 base and this is with the ln, and the other thing we find that the parameter C is any value other than 273.15 Kelvin. So, this equation is much more used. Now, coming back to the assumptions which were involved in Clausius-Clapeyron equation, despite the fact that it has been so successful and it is used so very frequently, possibly it's thought that a fortunate cancellation of the errors inherent due to the different assumptions gives, or it's responsible for the success of the Clausius-Clapeyron equation. Now, what is the most drastic assumption? I had just mentioned it in the last class. The most drastic assumption is that I have assumed delta H vaporization to be constant, based on which performed this particular integration in coming from this equation to this equation. In reality, we know that delta H vaporization, it is a significant function of temperature, and this will be evident if you observe the PV curves which I have shown in this particular diagram. We find that the liquid region exists in this particular region, the vapor region exists under this particular region. These are the isotherms which have been drawn, the constant temperature isotherms, and we find that there is a dome where the liquid vapor, both of them coexist. When any particular system is within this particular dome, then it keeps on changing its composition, it keeps on changing its phase from the pure liquid state to the pure vapor phase. It keeps on changing its composition from the pure liquid state to the pure vapor phase, and when it is inside the dome, we find that depending upon its location, it has different proportions of the liquid and vapor. We find that as we go towards higher and higher pressures, we find that this liquid vapor dome, it keeps on becoming smaller and smaller, and the horizontal portion which marks the phase change from the liquid to the vapor region, that keeps on getting shorter and shorter till it reduces to a point at the critical point. So, therefore, at the critical point, what we observe is the molar volume of the liquid phase and the vapor phase, they are the same, and therefore, none of the phases, they can be distinguished from one another, and under this particular condition we find that the transition is not abrupt, it is just continuous. So, therefore, accordingly, based on this, if we plot delta H vaporization versus temperature, we find that the curve is something of this sort, where delta H vaporization becomes 0 at T equals to Tc. So, therefore, from here it is quite evident that there is in no way delta H vaporization is constant unless we assume the two temperatures T1 and T2 over which the transition, or over which the phase transition takes place, are very close to one another. So, therefore, my next attempt will be to find out the dependence of the latent heat of vaporization on temperature, and this particular derivation, this has been derived from the this is known as the Kirchhoff's equation. We know that the latent heat of vaporization, this is nothing but equal to H vapor minus H liquid. So therefore d of this is going to give me this, right. Now this is the latent heat of vaporization, it is dHV minus dHL. If you recall the property during property estimations for pure substances, for single phase substances, that is in closed systems, we had related H with measurable parameters T and P. If you recall those equations that we had derived, dH was equal to Cp dt plus V into 1 minus beta T Tp, right, when we were trying to express H as a function of T and P. Fine. So therefore we can substitute this equation for the vapor phase and for the liquid phase in this particular equation. Once we substitute, what do we get? We get d delta Hv, this is nothing but equal to Cp vapor minus Cp liquid dt plus V vapor minus V liquid minus V vapor beta vapor minus V liquid beta liquid T into dP, right. We get this equation, and from this equation, suppose I would like to find out the variation of the molar latent heat of vaporization with temperature. What do we get? The equation is something of this sort: Vg minus Vl minus Vg, sorry, it's I missed, it should be Vv minus beta V minus Vl beta L T delta Hv by T delta V, isn't it? What I have done, I have substituted dH from the basic equation that we had derived, and then I had substituted the Clausius-Clapeyron equation for dP dt in this particular case. So from there, what do I get? I get d delta Hv dt in this particular case, it is nothing but equal to Cp vapor minus Cp liquid plus delta Hv by T, this and this cancels out, minus Vv beta V minus Vl beta L by Vv minus Vl into delta Hv. And this particular equation, this is known as the Kirchhoff's equation to predict the latent heat of vaporization in terms of temperature and pressure. And this can find, so therefore this is the equation. This is primarily for the liquid vapor transition. Now what happens for the, and in this particular case it is important for us to remember that if we assume that the vapor phase is an ideal gas, then for that case beta V is nothing but equals to 1 by T, and again if we assume that beta V is much greater than VL, as a result beta V will also be much greater than VL beta L, and substituting all these things here, we finally get d delta Hv dt, that is nothing but equal to Cp vapor minus Cp liquid. The other terms we find they are going to cancel off. So therefore this particular equation gives us the variation of latent heat of vaporization with temperature. Now suppose I would like to find an identical thing for the solid liquid transition. That in that particular case, suppose I would like to find the delta H fusion, then in that case here also I repeat the same thing, I do the same thing, I try to substitute dH L minus DHS, I write this in terms of CPS, CPL, etc., and then the equation that I get is CPL minus CPS plus repeating VL minus VS minus VL beta L minus VS beta S T into delta HF by T delta V, right. From where again if I start substituting, I get CPL minus CPS plus delta HF by T minus VL beta L minus Vs beta S by VL minus Vs delta HF by T. And if we assume that VL, Vs, your CPL, CPS, all of these are constant, and I also assume that quite naturally in both the solid and for the liquid they are incompressible fluids. So, beta is negligible. As a result of that, we in this particular case the equation reduces to delta HF by T, which is nothing but CPL minus CPS divided by T. So, therefore, from here what did I get? If you observe that we could actually predict the variation of the latent heat of vaporization and the variation of the latent heat of fusion with temperature in terms of the specific heats of the two phases. In fact, it is important for you to remember that when I assume that the latent heat is constant, it means that I assume that the specific heats of both the phases in the respective phases remain constant with temperature. And so, therefore, from these equations we can also find that we can predict delta HV at temperatures other than the normal boiling point. We can predict delta HV at temperatures other than normal boiling point using the Kirchhoff's equation. Okay. And I would also at the end like to mention a few other equations which can be used for these purposes. Those equations are primarily empirical in nature. One of the equations is due to Watson. It is known as a Watson correlation, which gives delta HV2 equals to delta HV1 1 minus TR2 by 1 minus TR1 to the power 0.38, where 1 and 2, these two refer to the temperature of states 1 and 2, and Tr is nothing but the reduced temperature, which is nothing but T by Tc. And for finding out the latent heat of vaporization at the normal boiling point, this is easily estimated from another correlation which is known as the Riedel correlation. From here we can find out delta HVN, it is nothing but 1.093 RTC TBR ln PC minus 1.013 by 0.930 minus TBR. So, therefore, what I mean to say is, and in this particular equation we find delta HVN, it is nothing but the enthalpy of vaporization at normal boiling point. Tc is nothing but the critical temperature, as we know. Pc is nothing but the critical pressure, and this equation TBR is nothing but the reduced boiling point, reduced normal boiling point, reduced normal boiling point of the particular substance with which we are dealing with. So, therefore, we can use the Riedel correlation to find out the molar latent heat of vaporization at the normal boiling point, and then we can either use the Kirchhoff's equation or we can use the Watson correlation to find out the molar latent heat of vaporization at any temperature other than the normal boiling point. So, with this I would like to conclude this particular session on homogeneous open systems, the simplest type of open systems which comprises of just one component and it exists in two phases, and we found by using the basic equations of thermodynamics, we could actually predict either the pressure temperature data from the thermodynamic data like molar enthalpy of vaporization or molar enthalpy of transition, or the vice versa. And from here we could also deduce two equations, namely the Clapeyron and the Clausius-Clapeyron equation. And I would like to remind you once more that the Clausius-Clapeyron equation, despite its large number of assumptions, serves quite well for practical purposes, but usually we use the Antoine's equation to find out the vapor pressure. In the next class, what we are going to do, we are going to deal with heterogeneous closed systems. So, initially what I did, we started our discussions with homogeneous closed systems. In homogeneous closed systems, we assumed that it was made up of a single component, or even if it was a mixture, the composition of the mixture did not change, and we tried to define a large number of properties for those particular systems, and we tried to relate the measurable and non-measurable properties, and the basis for that was Maxwell's equation. After that, we just relaxed the assumption further, we went for homogeneous open systems and we deduced the Clausius-Clapeyron equation. In the next class, we are going to deal with the heterogeneous closed systems, which comprises of a large number of homogeneous open systems which have been enclosed, or rather which are enclosed by a boundary, and the entire composite system does not interact with the surroundings with respect to mass transfer or with respect to volume transfer. It can interact with respect to energy interactions. So, we are going to deal with heterogeneous closed systems in the next class.